Good afternoon. On behalf of IIT Bombay Innovation Institution Innovation Council, I have great pleasure in welcoming you to this off-day workshop on World Creativity and Innovation Day. As we all know, creativity and innovation go hand in hand. So when we talk about research runs on four wheels: creativity, innovation, hard work, and perseverance. And between creativity and innovation, again, creativity for innovation, creativity in innovation, and creativity on innovation. So we have three outstanding speakers today. Two are our own, Professor Santosh Narana from Chemical Engineering and Professor Nishant Sharma from School of IDC. And we have a third speaker who is also our regularly visiting professor, Dr. Manish Agarwal. He will be the first speaker. He is a renowned orthopedic oncologist, currently practicing at Nanavati Max Super Specialty Hospital in Mumbai. He has more than 20 years of experience in the field of orthopedic oncology, and he is widely recognized as one of the pioneers in orthopedic oncology in India. He did his MBBS and MS from GS Medical College and KEM Hospital, and he did a fellowship in bone and soft tissue tumors at Tata Memorial in 1993 before joining as a lecturer at KEM Hospital. In 2000, he joined Tata Memorial as a full-time orthopedic oncologist and pioneered the field of orthopedic oncology in India. So he has received several awards, and if I have to read all that, I will be taking 10 minutes of his time. But what I'm really interested and conveying is he has been collaborating with one of our innovative mechanical engineering out branch, it is BETIC. He has been collaborating with Professor B. Ravi for more than 20 years, and he used to be a regular visitor to IIT Bombay. Dr. Agarwal.
So thank you very much for giving me a chance to talk here, and as told that I'm not actually an outsider. I'm quite an insider into IIT Bombay. In fact, my association with IIT began way before I joined medicine. I got admission into IIT Bombay. I was here for a few days till the time the medical admissions began, and you could choose only one field. And medicine was something which was more overpowering for me than engineering. But after medicine, I realized that doing orthopedics means it's all engineering. So we are back here with BETIC in IIT Bombay, and we've tried to do a lot of things to change the whole perception of Indian implants and the quality. And that's the story which I'm going to probably speak to you. So let me first tell you, what do I do? You heard about this word orthopedic oncology, but what does it really mean? It means that I deal with musculoskeletal tumors. Now, very few people even believe that you can get cancers or tumors which come from bone or soft tissue. They're so rare. So if you look at this graph, it will tell you that if you had 100 cancer cases in any cancer hospital, only 2 of them would be musculoskeletal. 1%, one of them will be bone and one will be soft tissue. So they're so rare that not much attention has come to them. But what has happened in the last 3 decades is a lot of advances have made these curable. And that's the reason the interest has come, because they affect young people between 10 and 25 years of age. And that's the reason why we've got interested in this. Now, to give you a little background of why this work which I'm going to talk to you about, I think you should understand what the background of bone cancer was. And I'm going to take you to 1920, where there was a big meeting on treating these bone sarcomas. And Sir Stanford Cade was a very big surgeon in those days, and he said these words to conclude the meeting. He said that if you do not operate, they die. If you operate, it used to be an amputation at that time, and they would die just the same. And he said, gentlemen, this meeting should be concluded with prayers. which means that there was really nothing. A bone cancer was a death sentence. And this didn't change for a long time. That was 1920. And I'm showing you a picture from 1993 when I was a fellow at Tata Memorial Hospital. Bone and soft tissue tumors was being a small part of the unit. So it used to be breast, bone and soft tissue. And my boss was a general surgeon. And every time we admitted a patient of bone cancer for amputation, he would go and look at the lifeline of the patient because it was a certain death sentence for them. Now, fortunately, everything has changed. Earlier, even at that time when I was doing my fellowship, the only surgery, like I told you, used to be an amputation and hardly ever any limb. Really didn't do much of limb saving surgery. But in today's day, what was no cure has become almost a 70% chance of cure. And we have between 80 and 90% rates of limb salvage. That means these patients get cured and they get a limb saving surgery. So what do we do in limb saving surgery? Again, to understand the background, we remove that bone with the tumor. Don't remove the limb. Preserve what is important. Preserve the muscles which are not affected, and then you have a gap which is reconstructed with a metallic implant which you see, and this is a prosthesis which we are going to talk about today. There is a big difference between the knee replacement which is done for arthritis, which you've all heard about, and a knee replacement done for tumors. The pictures on the left will show you what an arthritis replacement is. It is a resurfacing. So anybody who's had dental caps done after root canal knows that the dentist puts on a cap on the top of the tooth, and that's what's done for the joint, that the articulating surfaces are resurfaced into something smoother so that there is no pain. When you are talking of tumors, you're not just resurfacing, but you're removing entire segments of bone, all the ligaments, and therefore these joints are big and they're called as megaprosthesis. And they have a lot of stress on them, and because of which they also tend to fail much earlier than what a knee replacement for arthritis would. And that is what brings in the challenge of making these implants. Now, how do these patients function? This is an example of somebody who had a bone cancer, a 20-year-old. You can see this tumor there. Biopsy-proven bone cancer, given chemotherapy. You lose hair, as you know, in chemotherapy. These are the worst times for a 20-year-old because you are feeling so negative. You don't have any hair, you don't have any appetite, you've lost a lot of weight, and you don't know what's going to happen to your limb, and they never believe the doctors when we tell them that you're going to be quite okay. This is what was done. We removed the tumor, we replaced it with that metallic implant. She's gone on to become an air hostess with Indigo. Now, during her training, even when she was being selected, they have to go through a number of tests. They have to come down that slide and get up in that fixed time. And they could not tell that she's had 40% of her femur replaced by a metallic prosthesis. And today she's about 7-8 years after her surgery, and she's flying on the international sector where she has no problems related to this implant. So the question which will come is that, okay, the results are good initially. What happens in the long run? How long will these joints last? Because these patients are very young. So this is an example of a girl at 18 years after her surgery. No other surgeries have been required, and her joint is still working very well. Which means that if you had a good quality prosthesis, you can expect these joints to last for a fair amount of time. We tell them not to run and jump, but these can last for a long time and give you a good quality life where they can function as independent people doing all the kinds of work that they wish to do. The problem with these joints, you've seen two cases, and both of them had imported joints. They're expensive. Now, I took this picture About 23 years ago, I put that joint on the car because the car and the joint cost the same. So it's so expensive, it costs 4 to 5 lakhs, that it is out of reach of almost 80-85% of our patients. So what do you do for those patients, which is a large majority which can't afford these high quality implants? Do we have any affordable Indian implants? And we have a large number of patients who come to a hospital like Tata Memorial Hospital. So when I joined in the year 2000, it was required to have an implant which we can use for these patients. And we realized when we looked at the local implants that they were extremely poor quality. None of these were made with any attention to biomechanics. So they would have complications. You can see the joints which are dislocated, bent, and broken. Now this was okay because many patients would not survive the disease. In those days the survivals were very poor, so the patient would die and there's nobody who's going to tell the story of a bad implant. But if these patients survived, some of them did, the complications which came out of a bad implant were far worse than the complications from the disease. I mean, there are times when you wish that these patients actually had died because they have so many problems and many of them went on to an amputation. So these were just local stainless steel hinges made in local workshops and put in because there was nothing better available and the patient couldn't afford anything more expensive. So we required a good quality Indian prosthesis. Question was, how do you get it? How do you get a good quality Indian implant? Now these implants, as I told you, they require to withstand huge amount of forces, and it was not easy to develop that technology indigenously because our Western manufacturers, the multinationals, have spent a lot of amount of money and time in developing it and bringing it to a level at which they function very reliably over a period of time, and they're not going to share that technology with us. They don't want to give in a prosthesis at low cost because their mandate is to make money. And the number of cases, like I told you, it's so rare that the numbers that you need is never going to make it viable, even if they invest that money and make it. So how in the world do we could not get even a local manufacturer to get interested. Somehow, we forced one manufacturer who used to make plates and screws and nails to make one joint for us every month. That means 12 joints in a year, and that's how we actually began. So any medical device, when you need to make, I think somewhere you require that commitment that we need to do something for our patient, and that's the strongest incentive to develop something, and that's the story I'm going to tell you. And please stop me because if I overshoot the time, because we become passionate about this. All journeys begin with small steps, and like I told you, it was impossible to get something international class immediately. So it begins by making door hinges. Like I told you, one manufacturer, in the time that their machines were not used to make plates and screws and nails, would make these joints, stainless steel hinges on a hand lathe, and we would get one in a month. That's how it began. This is what it looked like in the year 2000. And we actually put these into the patients because we had nothing better available in those days. And mind you, anything that we made in those days would have been an improvement on the past. So even for these very inferior joints, we were actually given a lot of credit by the hospital. Okay, you did something, and we were very happy that, okay, we were able to do something. And they functioned quite well. In the short term, you could not tell actually any difference between this and the imported. You can't tell when you saw this patient walk whether they have an Indian joint or an imported joint. And compared to the cost of 4 lakhs, these were 15,000 rupees. That was it. So we were doing this. However, this was only the first step. We knew this is a jugaad. This is going to fail. And that's what started happening. So we had to actually team up with engineering. We realized very quickly that surgeons should not be designing the prosthesis. It's just like we say engineers are not going to do the surgery. I think doctors should not be trying to design the implants. So we got help. We started doing these meetings, which were engineers, researchers, and doctors on one common platform, trying to understand what is available in terms of technology and what doctors need, and try to bring them together into working groups. And that's how I met Professor Ravi in 2002. And we started working together because we have to improve these joints, bring in engineering input into them, and how much difference does it make? This is an example. In 2004, these pelvic tumors are probably the most challenging tumors for any of us. They're probably the most complicated surgeries in orthopedics, where you have to remove a tumor without removing the limb. So you have to remove a part of the pelvis and then reconstruct it back so that the patient is able to walk again. In those days, this is what is called as a saddle prosthesis. It would not anchor into the bone. It would just, like a saddle, take support on the bone and transmit the force. But none of the available implants would actually match with the Indian patient's bony anatomy. So what we did here, 3D printers had just become available in IIT Bombay. So we printed that bone model. You can see that we have put in M-seal inside to show where the tumor would be, decided where the cut will come, and then we made an implant which would fit onto that bone. 17 years later, this implant is still in the patient's body and this patient is still able to walk. All the other saddle prostheses in the world have failed, done everywhere in the world, whether it is multinational or made by us, but this has lasted maybe because it was sized according to the patient's anatomy. So, while we were doing these things, we got Professor Ravi, you can see, and his team into the operating theatre. And this was important because unlike what is done in engineering everywhere else, you need to understand that when you're operating, you have access through a very narrow corridor. You don't have all around 360-degree access. So you have to remove the tumor and implant the prosthesis through that exposure that you have. And once you understand that, then you can design instruments, you can design your implant, and then go ahead and make the improvements. So we started using the FEA to understand why these joints were failing, which were the areas of the stress points, corrected that, and maybe you have heard of this philosophy, the Japanese philosophy of Kaizen, where you do improvements in small steps until you get a significant improvement. And that's what we started doing on our joints. So you can see from 2000 to 2005, we made whatever small changes we could do without making a huge amount of cost, because I told you we were getting only one joint a month in those days. And in 2006, then we made a major change. And this Indian joint, actually 700 of these are done every year today in about 17 countries, though it's not the best joint. But we realized at that time that this is not going to do. This is only a stopgap. We need a world-class prosthesis. So we put together a project. We went to Department of Science and Technology. We went to Department of Biotechnology, and they both threw us out. Department of Science and Technology said this is an over-ambitious project and it can't be done. And Department of Biotechnology said it affects very few people, so we are not interested. So Professor Ravi and I started investing our own money and said whatever development we can do, we continue to do. So the stems which were breaking at that time, we realized that if you add a fillet to it, you can probably increase the diameter, you can reduce the chance of breaking. So all that we started doing, we made this prosthesis modular and converted the stems to titanium, and the rest of the prosthesis remained in stainless steel so that the cost could be kept down. This is the implant which I told you about 700 now are being done annually. This is what it looked like, but again, this is not a good implant. All of these implants fail. Almost all of them fail in 5 years' time. So we had to change this, and that's where we needed a proper high-quality prosthesis like I showed you of the patients before. And actually, many things in life, and you'll agree with me, happen by chance. You don't never expect it, you don't know how it's going to happen. So somehow circumstances come together. So Dr. Bal Subramaniam, Director of Non-Ferrous Technology Development Corporation in Hyderabad, came into IIT Bombay to Professor Ravi's office, met us and said, I want to be a part of this project. Now we had somebody who could actually manufacture the joint if we had a design, so we got together. That's Professor Bal Subramaniam, that's Professor Ravi and me, so the three of us started working on this together. And in 2005, the Golden Jubilee meeting of the Indian Orthopedic Association was in Bombay. And we had Dr. R. Chidambaram, who was initially a BARC director and then became the principal scientific advisor to Government of India. He came as a chief guest. And during his speech, he kept asking this question, why don't we have high-quality Indian implant? And like I told you, as luck would have it, I had won the Best Paper Award the previous year, so it was given to me by him this year. So he asked me this question backstage, why don't we have high-quality Indian implants? And I told him, we want to, but your agencies don't support us. So he called a meeting in IIT Bombay of about 22 working groups which were working on orthopedic implants all over the country and asked everybody to submit a roadmap, give in a project, tell what is required. And we were the only ones who submitted. We had asked for 20 lakhs, like I told you, to do the project. He said, I can give you 5 crores. And the only condition is that it should not remain in the lab, it has to go into the body. So that was how this project started. This is the AutoCAD project, and we started this work. This you can identify, it's there on the campus. It's now the Betic, we call it the tin shed, which was there. It is still there, and I think it is going to be a heritage structure because we don't want to remove it. There's a lot of development coming behind it. But that's the story of how we started. We got funding there, we got equipment there, and we started improving these joints. Now, we had no way of getting knowledge which was already got by these multinational companies. So we did everything from scratch. We got our biomechanics, measurements, understood all the implant failures because we didn't want a joint which was going to fail in the same way as the others were failing. We also improved the surgery. We went through every joint. We saw about 20 joints from all over the world made by different companies and analyzed each one of them for failure. So this is the list of our requirements which were there. It has to be a rotating hinge because these are the ones which last, not a fixed hinge. It had to be made in titanium or chrome cobalt because these are much stronger materials and will not break. It had to be modular. And what was important from our surgical point of view is that all the assembling of the joint and disassembly, if you had to change it, had to be from one side where you are making an incision into the body. And that is something which took us a long time to design the joint for. But today's joint actually is like that, and therefore it is superior to the other joints. And the polyethylene which you see, apart from the metals, you have high density polyethylene as one of the surfaces on which the metal articulates. That has something where we should not wear out, and the problem so far with all Indian joints had been is that used to be the reason for failure. So we had multiple designs. There were some 18 different designs which were made and discarded. Finally, it was the 18th one which was accepted. So you can see all these prototypes which were made, a lot of effort went into each one, and then we suddenly found that it didn't fulfill one of the requirements that we wanted and discarded. That is the time when I think this statement counts, is that even though you keep getting failure after failure, you will still have to persist till you finally hit on the right design. And finally we got this particular design, and this is something which had never been done in the world before. It's a totally different concept which had this kind of an axle where there is a rotation around that central ball on that pin which is there. Now we had the design It was something which could be manufactured, because that was another important point of the design, that it should be possible to manufacture it, whatever you have designed it. We also wanted the prosthesis to fit Indian anatomy. So we had to take all the measurements. We did all the anthropological measurements so that we could decide the sizing for the Indian population. And we finally had this, and you can see that approval. I have signed it out because they said that now if you change the design, we are going to send somebody to finish you off, because they were so frustrated at the end of it. But we finally accepted this design. We had our modularity, all the components very quickly. Again, we had to optimize that design using the FEA first. The polyethylene, like I told you, was the biggest problem, because we had to learn how to machine it, and we realized that temperatures, humidity, all that made a difference to the quality of the poly and also the raw material. Which means once we decided to accept the poly, we had to buy the entire stock that we are going to need for the next 10 years, so that there is no change in the batch or the raw material which comes in. All that was done, the casting was worked out. The way to reduce the cost was to use centrifugal casting, which would cost only 10% of what the otherwise hipping would cost. So all this was done at the NFTDC along with the polymachining, working out how to get that design correct. You can see here the scanning electron microscope pictures on the top and bottom is how the machining actually changes the surface roughness. And this was what was going to be important to keep the joint lasting for a longer period of time over millions of cycles of loading. Now the HA is also an interesting story, because different powders had different ratios of crystalline and amorphous HA, and their composition changed. So you could not get a uniform material to do the plasma spray. So finally we had to synthesize our own HA in the lab and use that for the plasma spray on the collar. We did the virtual testing first, as you can see here, and then we actually had to build a simulator, because if we bought the simulator, all our 5 crores would have gone in buying the simulator. So this became another project. We built this knee simulator to give the same forces which come on the human knee over 10 million cycles of loading first and then 20 million cycles. Very often we realize that the simulator failed before the joint. So we have to keep improving that simulator. That is the reason why a project which was supposed to take 3 years actually took us almost 9 years to complete on that joint. But finally we had this simulator built and we tested the joint and we realized that the poly was withstanding. You could weigh the poly before, after, measure the surface roughness and prove that the poly wear was very little in this design. We were now ready with the prosthesis. We had the design, we had the prototype, and we could now go on to the clinical trials. This is a very short video showing the manufacturing process, and this also had to be optimized because we had to learn how to use that 4.5 axis or 5 axis machine to engineer or to machine that complex shape which that femoral condyle has. Use the surface finishing using a robot. Now all this would not be covered by the cost of the project. So NFTDC actually used their other projects and equipment from other projects to bring it onto this prosthesis so that we can have the best of technology. Again, they developed this whole system of plasma spraying by buying a second-hand gun from somewhere, redoing it, refurbishing it, and making it useful for our prosthesis. We also designed instruments. Some of these were for the first time in the world, and we got them patented as well so that the surgery could be done precisely and fit in. Now, these are the 3 different joints. The first one is the Indian joint which we were using at that time. What you see in the center is the imported joint which is used all over the world even today. And that's the benchmark that we used. And what you see on the right is our new design which we call as TKP 2.4. That's the looks of the joint. The first joint which is the restore, which we say is a fixed hinge, and as I told you, it's not the best quality joint. It has many limitations and it fails quickly. The one on the right is the GMRS, which is our benchmark, and That's the joint which the other two patients which I showed you initially have, and what we were trying to emulate. And the center is our joint. There are many unique things about this design. This is the only joint which actually has some weight on the tibial poly and some on the axle, so that the entire weight doesn't come on the axle. Also, you will see that the rotation, the center of rotation is not below the tibial base plate, but is in the center of the joint which you see here, which is very anatomical, like the natural knee. It also locks in extension and gives you only 5 degrees of rotation, so that the patient is pretty stable soon after surgery when they start walking. This is the first patient that we did 5 years ago, 2019 April. This was the tumor which was removed. These are the pictures of the implant inside. That's the post-op X-ray. I just seen him today morning before I came here, and this is his 5-year follow-up. He walks very well. His joint has very little amount of wear which we can test by a mediolateral laxity. He's got a little bit of laxity, but in 5 years' time, all the other Indian joints had failed, and this one is still going good. And you can see from the X-rays that you don't really see any sign of wear on the polyethylene bush. So what we've learned is, if you do not go after what you want, you will never get it. So we have to. It doesn't matter which agency tells you that it is too ambitious and can't be done. I think if you want to get it done, it happens. So everybody asks, what are the lessons that we learned from this? I think we all have to have realistic expectations. This is not going to come quickly. This kind of an innovation takes a long time. There are many challenges which are unforeseen, and you will have to be ready to face those challenges. We need patience. And if you have the government funding, then you don't pass on the R&D cost to the patient, and you can keep the cost of this joint low. This joint now is costing about 1 lakh rupee compared to the 5 lakhs of the imported, and it is actually superior to the imported joint in many aspects. 56 of these joints have been done now between Tata Memorial Hospital, AIMS, and what we have done, and we've not had any failures related to the prosthesis itself, and that itself I think is a heartening thing for us, because that is what will give us the permissions to make this available to everybody. The benefit is not just the joint, but what all it has created. It has allowed us to create this environment. We had this AutoCAD lab, which has now become the Biotechnology Incubation Center in IIT Bombay, which itself has now about 20 different devices which have been commercialized, and they keep taking every year some more devices. So a lot of people now have some kind of a facility where they can come with an idea, convert it into a device, and if possible, make their own startup, commercialize it. Now, what are the other things that have come out of this? You can see there's so many devices which have come, whether it's a biopsy gun or the stethoscope, smart stethoscope, and all that, which have come from this laboratory. What is relevant to us is, while we were talking to students at that time, we gave them a challenge that when we look at X-rays, we try to convert it into a 3D bone model into our head. Can we not have a software algorithm do that to us instead of having CT scans which are expensive? So there was a group of students who took it on as a challenge, and they were the first in the world to actually make that algorithm and show that the 3D models which were created from just X-rays were within a millimeter accuracy of the CT scans. And they formed a company called Algo Search, and they started working. Now you can use these 3D bone models for planning deformity corrections. Earlier we used to plan all this in 2 dimensions. Now you can plan it in 3 dimensions on the bone. And it's not just deformities. You can use it to do your arthroplasty planning, which again was done 2-dimensionally before, which means that before doing the surgery, I know what components I'm going to use and where my cuts are going to be and how I'm going to plan those things. And you can actually make custom-made 3D printed guides using just X-rays. That's the kind of planning we've done for this prosthesis which you see, again using that same software. So innovation in medical device is not just about technology. I think the whole thing is about creating solutions that are going to change or address the real world challenges. Every step you have to innovate. I'm going to end by just showing you this one case which was in the sternum, in our chest wall, in our breastbone, a tumor. And when you remove that tumor, you have to reconstruct it back, and you need something which is different from what has been done before, because it should not fail. It's going to cover the heart and the lungs in the front. So this is something which we designed, totally made in India at a cost which was very affordable. And this is now 2 years since we've done it, and the patient is fine and the implant is holding well. We've actually put up 3D printers in our own hospital now. We're making software that will not require doctors to require engineers to build their 3D printed jigs. Currently, we have an engineer who works with the doctors and converts it. So within about 48 hours from you needing a bone model and a cutting guide, that can be done within the hospital itself. Because we have to go this way, the cell phone technology way, where there is something for everybody at a cost which one can afford. So though the technology is high-end, I think what costs cutting guides which cost 5,000 euros are now 2,500 rupees for our patients because of this innovation. And these are all the people, you've heard about the three who built the joint, but I think these two, this is Nirmal Panda from NFTDC and this is Rupesh from IIT who's handling Betic now. These two are putting unbelievable amount of effort in doing all this. In fact, Rupesh's PhD thesis was based on one aspect of the joint, about the quality of the joint and what are the parameters to tell you that this is a good prosthesis. And this is all the team which has worked on it. This is our biggest challenge, was getting FDA approvals for a prosthesis, because this is a high-risk implant and we had that metal-on-metal failures coming in that year and nobody was willing to give us permission to use an implant which has never been tested before. But we finally convinced them with the simulator data and we got that done. Thank you. Sorry for exceeding the time, and will answer any questions.